Hello. Let's continue talking about. Um, this is lecture 4, in fact. So, sorry, I'm fixing this right now. So this is lecture 4 in Applied Nonlinear Dynamics and Nonlinear Control. We're still at the going through the basics of Applied Nonlinear Dynamics. So we have talked about discrete systems or maps, and for these kind of systems, or the system is essentially described using maps. In other words, we had, for example, on the left hand side we had xk plus 1, on the right hand side we had xk. So in other words, we go from current state xk to xk plus 1. Now we're going to talk about the basics of continuous time dynamical systems. DS stands for dynamical systems. That is differential equations. So continuous time dynamical systems or differential equations. So we use differential equations to describe systems where the state of the system continuously varies with time. Like, for example, mechanical oscillations, chemical reactions. So if you write down the equation for a chemical reaction, then you can describe how the concentration of each component of that chemical reaction varies with time, and then you can develop a differential equation describing the change in that particular substance by time. And then so we said, all right, we're going to talk about continuous time dynamical system. Now, continuous time dynamical systems are also divided into two groups. The first group is non-autonomous systems, and the second one is autonomous systems. The difference being, non-autonomous systems, the system does explicitly depend on time. So you're going to see, for example, the system has a force which is described using cosine omega t, and then time essentially appears explicitly in your dynamical systems. And for autonomous systems, this is not the case. So autonomous systems are autonomous. They do not need that explicit dependence on time. F is again our vector field. It could be linear, it could be nonlinear. Rn is our state space. X belongs to Rn, our Euclidean n-dimensional space. And then we have phase space. So if half of the variables are the time, if you obtain half of the variables on the left hand side by differentiating the other half, displacement, for example, and velocities, then that's called the phase space. We have integral curves, which represent a solution of non-autonomous systems in extended space. Extended space is the space, your Euclidean space, your Cartesian space, including time. So if you have also this time, and time belongs to R, real numbers, then this is an extended space. And if you describe your solution in this space, you get a curve, for example, which is an integral curve. It's called an integral curve. And F, as you might guess, describes the tangent vector at every point. F is equal to x dot, right? Therefore, at each point, F describes the tangent vector to that integral, to that solution of dynamical systems. And then we are mostly in nonlinear dynamics and nonlinear control. We also have control parameters. Control parameters, let's just show them separately. M, we are following right now the notation in Knife and Balachandran. So M belongs to Rm, m-dimensional Euclidean space. Therefore, f is a function from Rn. Rn is because x belongs to Rn, and then time belongs to R1, and m belongs to Rm, and it goes to Rn because on the left hand side we have Rn x dot, which was an n-dimensional state vector. Now let's consider, we have a few more definitions. Let's consider the domain D of x and t. So our domain includes both state vector and time. If f is C0, so we have already talked about C0 and C1. If each component of f, because we have in general more than one equation, and we can replace then f with f1, f2, f3. So if f, meaning that each component of f is C0, then that guarantees a solution, the existence of a solution to this differential equation. If f is also C1, that guarantees uniqueness of solution. There's only one solution to this differential equation. So C1 is when we differentiate each component of x f with respect to x and t, and then each component is continuous in this domain, then that guarantees a uniqueness of solution in that domain. And if f is both C0 and C1, that guarantees the system is deterministic, meaning that we only at every point in this domain we have definitely one solution, and that's the only solution. So there is no probability involved. At some point we're going to also talk about stochastic systems, but at this point you're talking about deterministic systems. Our function, our vector field, is both C0 and C1. All right, an example of non-autonomous system is our periodically forced non-or linear oscillator. So you can simply write down the equation of motion. At this level, you already know to do this. You can quickly realize how to write this equation of motion. So f cosine omega t on right hand side depends explicitly on time. Therefore, a system is non-autonomous systems. And now autonomous systems, AS, is x dot f, x, and m. There is no explicit dependence on time. In other words, the system is time invariant or time independent. If means that, it implies that xt is a solution, therefore x at t plus tau is also a solution. Think about it for a moment why it's the case. It's the case because you don't have any other function depending on time. If you look at this non-autonomous system, it matters what tau is. So on the right hand side, your forcing is not necessarily the same. So for t and t plus tau. So but for autonomous systems, this is always the case. So f at x m is always the case, either a t or a t plus tau. And at the end, the last thing is if f is CR, again, it's about, so we said that C0 and C1, when we differentiate each component once and we examine the continuity of each component, and CR is when we differentiate the function R times and then we examine the continuity of each component of this function. So if f is CR of x and m, then xt, the solution to this dynamical system is also CR of X and F. An example of an autonomous system is x1 dot is equal to x2 and x2 dot is minus omega x squared x1 minus 2 times mu x2. Alright, again, this is a graduate course, so you can quickly see what this system represents. This is an unforced periodic oscillator. So, and because we have damping, we know that at some point the oscillation goes to zero, because the energy of the system is damps out by damping in the system. And that's the short lesson for today. See you later.